Thanks, Lexi and Jake. Thanks for having me here. Happy to kick off this two-day workshop on near-term quantum devices. And I guess I'll say at the outset, we'll hear today and tomorrow a selection of presentations from both experimental and theoretical perspectives. On the experimental side, there are a few technologies that are sticking out now, and I would say in atomic physics, using atoms as qubits, I suppose we haven't really, well, I don't want to speak for everybody, but I haven't really thought that the term NISQ is super remarkable, because in atomic physics, we don't really take error correction very seriously yet, because we don't need to. The passive errors in atomic systems can be very, very low. Maybe not low enough, we don't know yet, but I'm pretty sure that we can get pretty wide and deep circuits, certainly well beyond quantum supremacy, where you can't simulate the behavior of the system on any classical computer. And I would say not unlikely, even without error correction, to be able to hit applications that are actually useful. We'll see how that goes, of course. So we've been thinking about this for a long time, how to string together gates with passive, you can call it passive error correction, just designing your system right. And this is an illustration of that, where the qubits here are each individual atoms, all of the same isotope of the same element, so they're perfectly replicable. A lot of this technology comes from atomic clockwork, certainly where I got my start in this field. Because they're replicable, in a sense, they have the first requirement for scalability. Well, they're replicable. You don't have to worry about inhomogeneities. When these qubits are left alone, the idle errors, I won't say they're zero, but they're as low as we'll ever need them to be. If they need to be 10 to the minus 6, the idle errors, we can do that. They're atomic clocks. We can get them by some measure replicable and good down to 10 to the minus 18. We don't need, fortunately, we don't need to get anywhere near that. So that's the one, right there is a couple of recipes for scaling, is that you have replicability, and that as you make the system big, you don't have to worry about the idle qubits, because they're not going to lose coherence. We don't really speak in terms of T1 and T2 in atomic systems, because they're as long as you need them to be. So it comes down to, and this is sort of interesting, it comes down to, it sounds like a cliche, but it comes down to engineering. The entirety of our error budget we understand, to maybe a part per million. We understand the errors, and they all have to do with the control system, every one of them. And in this case, for trapped ions, the control system starts with the trap itself, which are a bunch of electrodes that hold voltages, and they have to be controlled pretty well. But we understand how that's going to scale in the near term and over the next 10 years or so, because they have nothing to do with quantum physics. The other controls will be, in this case, in this particular case of atomic ions, we use laser beams to affect quantum gates and entanglement, and also other lasers to measure and initialize the system. I'll talk a little bit about that and hopefully branch out into a few of the small applications that we've demonstrated. So I'll talk on behalf of both my research group at the University of Maryland, but also just down the road from here, the startup IonQ, which is developing commercial ion trap quantum computers. Okay, so I won't spend much time on this slide. In fact, it's somewhat outdated, even though it's only a few years old. This is extracted from a review in Science of a few of the technologies that are starting to spin up. They're looking like we can maybe build small systems out of these technologies, from atoms and superconductors in particular. We'll hear a lot about that today and tomorrow. Within atomic physics, I already hinted that we have these atoms behaving as individual qubits. The qubits themselves are actually atomic clock levels, so we pick pairs of levels in an atom that, in this case, these are the ground state levels in the ytterbium-171 isotope, which is remarkably simple. The quantum numbers of the low-lying energy levels are exactly that of hydrogen. So we have a pair of levels that have very small magnetic field shifts, because they're m=0 states. So we get a lot of passive control that way. And the energy splitting is Planck's constant times this 12.6 gigahertz. That's the atomic clock. I could write it out to a few more digits if I wanted. So this is where we store our information in terms of qubits, and we can measure, in all atomic systems, we measure the qubit and initialize it through dissipative optical pumping or fluorescence techniques. And they're very good. They're as good as you need to be. Measurement per qubit can be more than 4 nines, and there are ways to get even more than that. But again, if you don't have 10,000 qubits, you probably don't need 4 nines. So you keep all the number of nines at bay, and of course work on the lowest one. The control of the qubit is somewhat interesting, and here's where we start to branch into engineering. Now, I've been inside lasers my whole life, and I'm happy to say that the control laser of ytterbium-171, we don't go inside that laser because it's at a wavelength that is industrial. 355 nanometers is, in a sense, the optimum wavelength to think about controlling coherently these qubits, and this laser is produced for the lithography industry, for making CMOS masks and so forth. So it's made very well. It's research quality, but I wouldn't call it a research laser. It's fixed frequency, and that suits us just fine. And there's the only adjustment. It's the on button, I like to say. And so it's part of the system, and it works for years. You just buy it. You can buy as much power as you want. I won't get into too many details. This is actually a pulse laser, so it produces a spectrum, which is a frequency comb, and that's really important because it allows us through a 2-photon transition to bridge the qubit and do control operations. But the laser itself is very passively stable. We stabilize it further, of course, but right out of the box, it's very good. Okay, so I'm going to talk a little bit about how we wire up these individual atomic ions. It is by, it's arguably the cleanest system right now in terms of control. We know how to generate entanglement over medium-sized systems, and I'll comment on that. So briefly, I'll talk a little bit about the circuit model. Of course, all this is pre-error correction because the fidelities can be very, very good. So I'll tell you how we generate entangling gates, 2-qubit entangling gates. Now, this is a little bit of a hand-waving argument. In some regimes, it's actually accurate. In others, there's some more details that I'll cover in due time. The idea here is if you have a line of atoms, and by the way, they're separated by several microns. We can obviously resolve them optically because the wavelength is much smaller than that. If we want to entangle any pair of these qubits, we can apply optical tweezer forces on that pair. And we do it in such a way with the laser that the selection rules give us a qubit state-dependent force. And for simplicity, I'll assume this force is transverse to the chain. For technical reasons, this is really what we want to do. These are the stiff modes. They're high frequency. They're lower noise. They're easier to control. And when we tune this laser just right, if we use spin up and spin down qubit language, and in this drawing, spin up receives a kick upward and spin down receives a kick downward, then you can see that depending on the state of these 2 qubits, the Coulomb interaction will be modulated. If they're both spin up, they will move up together, and their Coulomb interaction is the same as it was. Same with spin, if they're both down. But if they're in opposite spin states, they're a little further apart, and the energy defect, if you assume this little displacement is tiny compared to the separation, and it's nanometers typically, then you can expand this defect and you get an effective 1 over r cubed type interaction. And then when you write down the 4 possibilities of these 2 qubits, you see that there's a nonlinear phase shift because when you had mixed states of spin, you get the same energy defect. And this, when that phase is set to pi over 2, is as powerful, as expressive as a controlled NOT gate. So it can form part of the universal logic family. Okay, a few more details now. And this actually is accurate physics if this force is applied really fast. If you do it super fast and then you return the atoms much faster than any of the normal mode frequencies, which are, by the way, a few megahertz. So as long as you're really fast compared to megahertz, the physics is accurate. We're not faster than a megahertz. We're actually a little bit slower than a megahertz. So in fact, there are normal modes of motion you have to deal with. This is a very interesting thing. This is really classical physics. And again, I don't have time to discuss too much, but we can apply laser pulses and shape them using classical techniques to pre-calculate the pulses so that all these normal modes cancel at the end of the gate. So it's as though we did it in this ultra-fast regime. The trick is you're adding classical complexity, but again, this is, I don't want to trivialize it, it's engineering. There's nothing quantum about modulating a laser in just the right way to apply the force the way you want. The good news is when you do that, you're coupling to all these normal modes, and these normal modes are non-local. You don't have a 1 over r cubed fall off anymore. In fact, it's infinite range. So as long as you can deal with all these normal modes, you have an all-to-all connectivity. And this is incredibly efficient when it comes time to taking a real problem and compiling the gates to realize an algorithm. The gate count actually can shrink instead of blowing up if you had a nearest neighbor graph. The other sleight of hand is that we don't do this gate in the z basis. The spin-dependent force is actually in the x basis. It's sort of a detail. Sometimes it's called a Mulmer gate. It's based on physics discussed a long time ago by Serac and Zoller in a different regime. Sort of the same idea. You're modulating the Coulomb interaction between ions to make entanglement. So this is the native operation that pretty much all ion trap systems use. It's an XX gate. Sometimes we call it an Ising gate, but it's as expressive as a controlled knot gate. And the typical times for these gates, I said they're slower than a megahertz, so the typical times are tens or maybe even longer, microseconds. The fidelities, again, right off the bat, they can be, it's not hard to get in the high 90%, but the important thing is even at 98%, that 2%, we know where that noise is, and it's not fundamental. It's not a T2 process. It's always induced noise from the laser beam that's controlling the system. So we sort of know what the error budget is. Okay. So with that, we have built several systems, both at the university and also at INQ, to execute algorithms, small algorithms on small systems. And it's actually become a little bit of a user facility in a certain sense over the last several years. And these are I think all of these are from the university only over the last many years. And what's interesting is people from all walks have come to us wanting to run circuits. Admittedly, they're small circuits. At the university, we're limited to under 10 qubits right now. And we've been running things, and it's almost like going to school again. A lot of condensed matter physics behind these. But also, Jake mentioned metrics and benchmarks. We're running small algorithms that are sort of useless on their own, these oracle algorithms like Bernstein-Vazirani, but they're really useful for testing the overall fidelity of a system. It's just a single metric. Did it work or not? It's just a binary value, but it tells you something about the connectivity of the system and the fidelities of the aggregate system. Again, I don't have time to talk about many of these. In fact, I'm probably running out of time already. I'm going to skip this one, a circuit on testing whether unitaries scramble or not. There's a recent paper that describes this. But I want to move on to, very recently we've been thinking about dynamical circuits. That is, circuits that we can use classical feedback to optimize in a certain way. And this is finding a lot of use in many different types of algorithms. Some people use the term machine learning here. In this case, the machine learning is really on the classical side, where you somehow optimize the classical parameters and all the gates for a circuit to do something, maybe to make a state or to optimize some function, to minimize a cost function. In this case, again, lower your sights. This is a 4-qubit system where we're trying to make just a particular quantum state. With 4 qubits, there are 16 basis states. And we want to make this particular superposition equally weighted, 1/6 population each. Sometimes it makes connections to bars and stripes in terms of images, but again, there's only 4 pixels here. But these 6 states selected they have symmetry. They either have bars or stripes in them. And the question is, how do you make that state? It's actually not obvious how to make it using gates. If you write down the quantum states, it's pretty complicated. And of course, if you make this a 3x3 or a 4x4, it gets even more so. So with our 4 qubits, they're fully connected. We applied gates in a certain pattern where each one of these boxes has a classical parameter. And this is one layer, say, of a fully connected system. And we're using all 6 2-qubit gates here. We can also run different connectivities. So in this connectivity graph, we're missing some entangling gates. We might expect this layer of a circuit is probably not enough, at least in a single instance, to make this state. And we do, that's borne out in the data. We need to apply that one twice to make an arbitrary state. And again, the idea here is to, with our ions, to make some measurement. This is the target state. Derive some figure of merit, some overlap, some variance, some separation between the 2 distributions if you want. and then go to the classical computer and try to optimize 20 or 30 parameters. Very difficult to do that, even with 4 qubits. And then apply this standard circuit with different parameters and go back and forth. So this is sort of a loop. We're finding this a lot in variational quantum eigensolvers, quantum approximate optimization algorithms, and so forth. And very, very quickly, the classical optimizers can actually limit the whole system, even with 4 qubits. In this particular classical optimization called particle swarm, it's not so efficient because we're randomly picking out places in the phase space of all these parameters. And after many iterations, this is not the number of layers. This is the number of iterations in a given number of layers. I think these are all, oh, here we go. A here is 1 layer of full connectivity. This is 1 layer of reduced connectivity. This is 2 layers of reduced connectivity. And the range here has to do with the sampling of the particle swarm. There's some error bars in theory. And the experiment in blue, we see that if we have reduced connectivity with only 1 layer, as I promised, we're not going to get down to the 0. By the way, this figure of merit, you want it to be 0, the sort of the distance between the 2 states. And it starts to make it, with 2 layers of this reduced connectivity, we expect it to start to converge, but it's just super slow because this optimizer is, I think there's 26 parameters in this fit. Very hard to do that. It turned out a Bayesian classical optimizer worked a lot better. Maybe not a surprise for those of you that are actually professionals in optimization. And in this case, the experiment in theory, there's no error bar on the theory because there's no distribution of trial states to begin with. And you'll notice after only a few hundred instead of more than 1,000, we do converge into the correct state. So you can sort of see the distribution of the final states is very close to what we expected. Again, kind of a toy model, but to me what's neat is that we're now adapting a quantum circuit using optimization of the classical parameters that drive that circuit. Seems to be a theme in a lot. A more recent experiment, we've used techniques from QAOA with a few more qubits to create states, interesting states, subject to this Hamiltonian, which is a transverse Ising model with nearest neighbor connectivity in a ring. Here's sort of a circuit you might apply. So here in QAOA fashion, we apply the first part of the Hamiltonian and then the second part. The field part are just rotations. And we have sort of a ring of nearest neighbor identical Ising operations. So there's actually only 2 angles in this because these are all identical. If we, at the critical value of g equals 1, there's this phase transition. And at the critical value, the ground state, in a sense, is the most interesting. We use QAOA techniques to find that ground state. We expect theoretically that with 3 layers of this circuit, we should be able to get the exact ground state. And this is sort of data with 1 and 2 layers of this circuit here. Again, minus 8.8 is down, all the way down to the bottom here. We didn't quite make it with p equals 1 as expected. P equals 2 is a little worse. So this is telling you that even with 7 qubits, and I promised the gates were so good and so forth, even with 7 qubits, we're seeing that things get a little worse as we add layers. So we didn't even do p equals 3 in this case. By the way, this is in collaboration with Tim Say at Perimeter and Sonic Ajori at Intel. We use the same type of a circuit to make another type of a state that I just learned about not too long ago called the thermal field double state, and under the same Hamiltonian. The thermal field double state is a partitioned system that is just a straightforward thermal state when you trace over either system and look at the other. But it's a pure state overall between the 2 systems, and it has these Boltzmann factors according to the eigenstates. So it's like a thermal state. It's sort of like a bell pair extended to thermal states under some spectrum of Hamiltonian. In this case, it would be an interesting Hamiltonian, the transverse field Ising model here. And in this case, again, this will appear on the archive very soon. In this case, each layer of the circuit actually has 4 terms. To realize this, I'm not getting into too many details, and I'll probably skip across this. This state, by the way, is motivated in black hole physics, thermal states. And when you have one that's hidden in a black hole and you have another one outside, if you want to think of the whole system as a pure state, this is one model of that. Making that entangled state, especially under a complex Hamiltonian, is pretty tricky. Again, sorry, I'm kind of running out of time here. Now going over to IQ and talking about benchmarks, I hinted that we're playing around with these Oracle algorithms, Bernstein-Vazirani. There's a hidden string, and in a single query, you should be able to find it with perfect efficiency. And so this is a 11 qubit circuit. One's an ancilla, and here we're hiding a 10-bit string with the pattern of gates here. You can clearly see what the string is, 110101101101. And in a single query, of course, you should ideally be able to pick out that state in this measurement scheme. And this is all 1024 circuits, and these are the success rates. And again, each Ising gate is let's see, each Ising gate is, in this case, I think it was like 98.5%. So the error sort of makes sense with this aggregate error at the end. And again, this algorithm is not useful on its own, of course, even when you scale it up, but it's very useful as a very simple metric to how well your system's doing. Now you'll see this is a little bit of a trivial circuit. You don't need full connectivity here. You do need every qubit connected to the ancilla, but we can, of course, make the ancilla any qubit we want. So I'm not showing all the data, but there are actually, I guess, 10 times 1024 circuits. There's 10,000 unique circuits here. And with that, you can test all the connections. So it's a very useful benchmark, and we'll continue hitting this algorithm as we grow our system. The hidden shift is another version of that. This was first suggested to us by Martin Rottler at Microsoft, and we did a smaller version at the university. It's a little more complex circuit, depending on the function that you're hiding the shift in. It does require more a non-trivial connectivity. It also classically requires exponentially more queries to find out what that hidden shift is. Now, at IQ, we've also been playing around with variational quantum eigensolvers in the molecular chemistry realm that a lot of the community is looking at. And these are theoretical, this is a theoretical table on how many qubits and how many gates you need to simulate the ground state of the water molecule using a standard VQE approach. And I'm shifting so we know the answer in water, it's minus 75 something Hartrees. And when we offset from that known answer with a deeper circuit in the VQE algorithm, we converge after maybe about 12 or 15 qubits. And you can see several hundred circuits, several hundred gates, we should be able to converge to the answer in H2O. Now, what's interesting about these first two columns is that the number of gates here is sort of the naive application of VQE. And without any approximation, given, and this assumes full connectivity, by the way. If you don't have full connectivity, that number will probably grow, especially as the system grows, maybe by the square root of the number of qubits you have. But in our system, we have full connectivity, and furthermore, we were able to compress it by about a factor of 5 because of the expression of our gates. And this is work Yongqing Nam at IQ and also Ken Brown at Duke really had a big hand in the Jungsang Kim as well. So this is all doable on current technology. Admittedly, we're just starting our march down there, but what's notable here is that the error bars, both systematic and statistical, are not so much different than the so-called chemical accuracy. This is basically KT. That's what you need to hit. And as we go deeper in the circuits, it's still small. We're pretty confident that we should be able to go all the way down here. Okay, so I'll also note that other molecules that have been simulated, after 2 iterations, they blow up. So things are not converging in these other technologies because the gates aren't as good and the connection is not as good in those systems. Okay, so I want to briefly talk about another type of quantum computer that we have in trapped ions that is actually a little easier in terms of engineering. Sometimes we call it analog quantum simulation. Instead of doing a pointwise Ising gate between pairs, we can, of course, apply a fully connected Ising chain by having a big fat beam. It's a lot easier because now we don't have to focus any laser beams. And beam fluctuations are much easier to deal with here. And we end up with a Hamiltonian, not surprisingly. It turns out to be an all-on-all Ising coupling. This is an approximation, but it's a long-range coupling where it's an inverse power law where alpha varies between all-on-all, 0, and dipolar, 3. And I'd say Alexei Gorshkov, our chair, is sort of a world's expert in these long-range Ising systems, and he's helped us understand some of the interesting phases that happen when you have such a power law interaction. We can add a transverse field, and to give you a sense of scale, There are no phonon operators in here because we're in the dispersive limit where we're far detuned, and so we can safely ignore we can adiabatically eliminate these phonons. The price we pay is that the couplings are slower yet. So instead of tens of kilohertz, it's about a kilohertz or so at best for nearest neighbor. And again, there's been a flurry of activity doing simulations with these magnetic systems. I won't get into many of these details, but with global beams, we have the opportunity to increase the number of qubits without super serious engineering yet. So at the university, we've pushed things to many dozens of qubits, up to 50 plus or so in a variety of applications. And since I talked about QAOA before, we have two separate experiments on campus. One is room temperature, one is cryogenic at 4 Kelvin that allows us to hold 100 plus spins. And the idea here is to, with our long-range Ising, transverse Ising model, prepare the ground state of this thing. And hopefully you're near criticality. And what critical means here is it's not B is equal to J naught because we have this long range, but we can sort of simulate where the critical parameters are in this Hamiltonian, and that ground state's interesting. Very small gaps, and there's high degeneracies and frustration and so forth. So here the idea, like before, is to apply these global layers. And what's nice here is that each layer only has one parameter now. We don't have to worry about all the individual gates. So in a sense, the classical side here is a little easier. We're going to alternate between these non-commuting parts of the Hamiltonian, and hopefully, with enough alternations, we can realize a pretty good replica of the ground state. Now, in the systems we're dealing with, we can do a lot of theory and understand what the spectrum is, and so our figure of merit here would be, this is a little tricky. This is the energy we get under these classical parameters divided by the bandwidth of the whole energy spectrum. So when eta is equal to 1, that means we've hit the ground state. When it's equal to 0, I guess that means we've hit the excited state. We went the wrong way. So 1 is good, 0 is bad. And when we start with a certain guess, in this case, we start with them all prepared in the X state. After a few iterations of, I think this is all, I think, just one layer. But after iterations of optimizing the parameters that go in there, it comes close, not to 1, but something that's a little below that. Again, theoretically, we understand what this error between whatever it is, 0.98 and 1 has to do with the fact that QAO is approximate, it's to A. It won't get you the perfect ground state. And of course, it's a smooth landscape when we look at just these two parameters in a single iteration. There's just one angle associated with that term, one angle associated with that term. And if we start in some place, we can use a gradient descent, simple gradient descent classical algorithm to find the ground state. And that's mapped right there. So I guess I'm going to step out a little bit and speculate on how we're going to scale the system. You might be disappointed that we're only doing circuits with on the order of 10, pretty soon about 20 qubits, and even our global operations are less than 100. I mean, those will certainly change, and I hinted at one of our systems, it's cryogenic, and we can load many more than 100 ions in there, and they stay there pretty much all day. And it's because we're not going cold to go cold. We're going cold to lower the pressure. So it's just cryo pumping at 4K. As a closed cycle system, it's actually not super painful. This picture is kind of fun because there is an impurity in here. It's probably a different isotope of ytterbium, or maybe it's in the F state, it's dark. But that gap stayed in the same position all day. That means there was not a single reordering collision in the system. So we're pretty comfortable with dealing with a few hundred qubits in this system. The real problem with scaling, you might argue, when you look at an AMO lab is this. And I see Dave Hayes in the audience. I don't know if you're in here. Maybe you're on the other side. But so this is actually an experiment I didn't talk about. It has 2 ion traps where we're doing photonic protocols to communicate and teleport information in this modular type of approach. But the fixed cost is enormous in lasers and the control of the system. And I mentioned that's the challenge. It's all about control. And this is a challenge. Well, over the last many years at the university, without too much of an exaggeration, we've put everything you see here in this box. It's a little bit of an exaggeration. We didn't put the students in there, for sure. But, the control lasers, the CW lasers are fiber-fed. Those are almost afterthoughts. But the control laser and all the coherent stuff, all the important stuff is in this meter cube box. And this has been forwarded through a big IARPA project that actually aims to error correct qubits, strangely enough. But to error correct qubits, according to a simple Bacon-Shor code, we need very high performance on the individual gates. And to get very high performance, we really had to start thinking about a system, not physics. So there's a lot of engineering that goes in here, and this is helped by Sandia that provides the chip. This is a drawer full of 6 CW tunable locked lasers, all fiber delivered. It's in a drawer. This is from AO Sense. Cold Quanta is producing not the vacuum chamber we have in here, but more experimental vacuum chambers that can be cryogenically cooled, and they're very small. So we're sort of applying this industrial approach to the individual components, and we're just integrating in the end. Coherence provides this laser I mentioned, the 355 laser, and I list them because we actually had to modify it. I lied, we had to get in that laser just to make a modification because they wouldn't do it at the factory, but they showed us how to do it. They lent us tools. So we now know how to do this to get increased phase stability in that laser. So this is a real system, and it's starting to produce, so you'll hear a lot more about this in the coming months and years. At IonQ, we developed technology basically based on this footprint. This is a picture of System 1, which has actually now been retired. At IonQ, there are 3 fourth systems on the way. And again, this is the picture I showed at the outset. It uses the same Sandia chip. And so to scale, you might still ask, well, how are you going to get beyond a dozen or so? Well, I didn't mention these individual beams that poke atoms. They sort of saturate at 32. And that has to do with the fact that our modulator only has 32 channels. We could increase that if we wanted. I don't think we're going to need to or want to because we have such a very fancy software package that we can move atoms around and scale this way. And this is illustrated actually when we load. At IonQ, we have an automatic loading procedure. Type in a number, how many ions you want, and there they are. They're with maybe a 75% probability. Each try loads an ion in the slot, and it gets shuttled over. They're zigzag, they get pulled out, we focus in, and we're ready to go. All in about a minute, and then we can take data on the system. Again, we only have 32 laser beams, and one way to scale, and this will sound sort of retro, but we know that we can put several hundred ions in a line. And even though we only have 32 laser beams, we can move the ions like a tape moving across a head. Now you might ask, when you have several hundred ions in a line, the normal modes are a mess. One thing we're learning, this is a little bit of a surprise, is that even though we couple to these normal modes, there's an emergent modularity that happens. And it turns out that we only have to deal with each ion and its maybe plus or minus 10 or 20 neighbors. So we abandon full connectivity, but we get to scale. So we can do a gate, it's not shown in this way, but we could do gates over here and here at the same time. They don't interfere. In fact, the crosstalk falls off like distance cubed. So as long as you are able to admit a tiny bit of error, you don't have, it's not a problem dealing with this long-range Coulomb interaction. That's really important. I think it'll get us to many hundreds of qubits using current technology. Now in the long run, I didn't talk about it at all. This is a sort of a concept picture. Once we can make modules, we can also go off chip using photonics to truly scale to hundreds, thousands, or even more. If you can stamp out these red boxes and get an efficient photonic connection, that's really the bottleneck. All of this stuff's classical. It exists. Optical cross-connect switches, beam splitters, and so forth, and eventually they'll be put on chip with waveguides and so forth. So our path to scalability, I would say we have the requirements, we have the initial sort of the demonstrations. It really comes down to just executing. And I borrowed this slide, you've probably seen it, from Hart McNevin at Google, the famous number of qubits, number of gates, or if you want, 1 minus 1 over fidelity or something like that. And as we scale, of course, we need to move up and to the right. Everybody wants to be up and to the right. It's not hard to move up. Sorry, it's not hard to move up and to the left. You can throw 1 million qubits together, but you can't do anything with them. That's not very interesting. And in ions, we can put 2 ions together and do 3 nines, or probably 4 nines, 5 nines. But with just 2, it's not so interesting. You really need to go up in this direction, and I think these black dots are sort of a range of different approaches with ions. These are not computers, but global simulators. We really think that in the coming years, we're going to clearly punch through this supremacy border and hopefully hit some treasure along the way before we have to do error correction, which may be when we have 200 or 300 qubits. Okay, well that's all I had to say. And again, a long list. A lot of these folks are in the room, and you'll notice a lot of them have gone over to industry. Even some of them somehow went to Honeywell. It's just, yeah, it's crazy. And this is a group at IQ. Many of them are here as well. Thanks for your attention.
Thank you, Chris, for an exciting talk and for being super on time. We have plenty of time for questions. John?
Could you say a little more about this emergent modularity of the normal modes? It sounds wrong.
Emergent is one of those terms that usually means you don't know what you're talking about when you say emergence, usually in the context of condensed matter. Well, so the basic idea in any number of qubits that we have is that and you should picture a bunch of pendulums connected by springs. When you have 1,000 of them, it's sort of a mess. If you wiggle one of them, forget it. So the information is lost to a classical thermal environment. But we wiggle these pendulums in a very special way. And when we hit 2 of them, we pulse shape the laser. And with up to maybe 100 qubits, we can actually do all the classical physics and take care of all the normal modes on your laptop. And it turns out each of the normal modes is excited. And at the end of the gate, we want it to be de-excited so that the normal modes are no longer entangled with the spins. Well, we've learned that by simplifying the laser pulses dramatically, maybe with only 10 control parameters instead of 100, we get within a whisker of perfect fidelity anyway. And we also see that when we look at the phonon wave functions, they're local. I should say an emergent locality or something. I mean, that sounds too fancy. But it was a little bit of a surprise. We thought this was a fundamental scaling problem. We can't put too many ions in one chain because then the information leaks. No. The phonons are phase coherent, and they can sort of interfere at the boundaries. So I didn't mean to make it sound more fancy than it is, but in practice, it's very important. It will allow us to go to well over hundreds of qubits without an added complexity in the classical control. The price we will pay, we don't have full connectivity anymore. It's going to be local 10 or 20.
Especially in the context of, say, VQE simulations and, say, especially for quantum chemistry, all the advantages of the ion-based platform that you described make this very attractive, like all-to-all connectivity, very low gate noise, and so on. There's one thing which is a little bit concerning, and that's like, in the end of the day, if you want to train the VQE, you have to do many repetitions of the experiment, and if your objective function is a quantum chemistry Hamiltonian, you need to measure a lot of matrix elements. And then the clock speed at some point starts to become a problem. And the clock speeds are, well, as you said, in the 100 microseconds or maybe tens of microseconds range. So is there any hope to improve that?
So the question has to do with clock speeds. And indeed, the gate speeds are at best a megahertz. They're typically a significant fraction of a megahertz. And in VQE and QAOA, yes, there's a lot of signal averaging. You can't just take a one shot here. The error bars I showed, we had to integrate, I don't know how long, it was probably a few hours or something. So yeah, it's a pretty serious thing. Now I would say on the one hand, there are ideas, in fact I said right at the outset, if we do this force really fast, it actually gets simpler, so we don't have to worry about all these phonons. And to do things really fast, I mean, we have fast laser pulses, you just need more intensity. So there's a trade-off there, and with more intensity come other just practical issues. So we have a research project thinking about ultra-fast gates. They're not as high fidelity due to the stupid mundane things, so we're not using them in the laboratory for these algorithms. So you're right, the clock speed's an issue. On the other hand, I would say maybe what's more important is the time to solution. And if you have a fast clock speed, but you can only do a couple of gates. And as you make the system bigger, you can actually do less gates. Clock speeds are relevant there, even though it's really fast. So Yeah, this is something that we have to think about. You know, Alexei and others think about in sampling experiments how to coarse grain, how to get observables by sampling in ways that are smarter. But this is an issue. It's a challenge, I think, in all of these eigensolver, these variational techniques. You need a lot of data. Thanks for. I didn't answer your question, but I agree. It's an interesting point.
More questions?
So for the quantum machine learning type things that you're doing with the like bars and stripes, you mentioned you have like 11 or 14 parameters that you're optimizing classically. I'm just wondering, like, how does this compare to like a purely classical algorithm that like does generative modeling of that probability distribution?
Somehow this is not displaying. So how does it compare to a classical? Well, it's a 4-qubit system. And what's hard about that system is that what is the circuit that generates that particular state? It's almost a random state. It's a pure state. I guess classically, I don't know. I mean, I can't prove there's not a simple analytic circuit that you can say you do these gates and you will make that state. I just don't know what it is. So the point there was not to compare the generation of the state with what you could do classically, because I don't know what that solution is. I think it more had to do with you know, straining the classical optimizers. More like 20, I think at the most we had 26 parameters we had to optimize in that system. And there we kind of couldn't do it classically.
I'm just wondering, like, order of magnitude, like, do you need a lot more parameters or like a lot fewer parameters for the quantum circuit compared to the classical, or like,
But what are you comparing it to? Compared to the classical what?
like just a classical generative model that models this probability distribution?
But it's not a probability distribution, pure state. It's a quantum superposition of these 6 out of 16 states spanning the Hilbert space.
Okay, but your goal is to get the probability distribution.
Well, the goal is to make this pure quantum state. Yeah, when you measure it, it's as though you had a probability distribution. I mean, if you want to make a probability distribution, just make each one of them with a probability of 1/6, just
Okay,
by
yeah.
dissipative means, I guess.
Okay.
So it's a little bit. I think I know what you're getting at. Maybe with 4 qubits, you're saying it's not very useful. I guess I would agree with that.
Next question?
Yeah, feel like making a stab at when you're going to achieve quantum supremacy? IQ, that is?
Quantum supremacy? Oh. Yeah. Well,
Not Wednesday?
Not Wednesday.
Not next Wednesday. Right?
Well, it actually ties into the last question. There are lots of things that we're doing now that we don't know how to calculate. It doesn't mean that somebody doesn't know how to calculate it. And my understanding of quantum supremacy, it has to be backed up with a rigorous proof that nobody can ever do this problem classically.
No, I mean, same algorithm done on a supercomputer versus on the IonQ computer. That's the comparison, not theoretical.
I guess I'm not so interested in that. I'm interested in something that's useful. I mean, when you get to 20 or 25 qubits, our systems will be faster than a classical computer could simulate the gates. Because the Hilbert spaces, I mean, you can still do it classically, but the quantum computer will beat it. The simulation of the circuit. Of course, the circuit needs to be interesting to really claim something that you'd call an advantage. So I don't mean to be dismissive. I mean, we all know that there's a number between 40 and 80. When you hit that number, you pretty much can't simulate whatever's going on. And so, we're going to get there. Others will too.
Hi. So you mentioned one of the things you want to do is prepare ground states of typical condensed matter models or spin models and so on. Analog quantum simulators also try to do that, and then once they make the phase, they try to classify the phase by measuring response, like, for example, transport properties. Can you elaborate on some of the things you can do with digital quantum simulator?
Some of the things you can do with...
Like what kind of responses? You can't measure transport, I guess.
Well, the simplest thing is to and this will tie a lot of things together. The simplest thing, when we started on this, and other labs did as well many years ago, was to try to adiabatically find ground states. So prepare the ground state of a trivial part of the Hamiltonian, adiabatically turn that down. And that works with some success, but to be adiabatic with an interesting Hamiltonian, of course, the gaps shrink. And so in a sense, this is what QAO is trying to shortcut.
No, I understand.
So we're measuring ground states, but you're asking about non-equilibrium processes, and we're,
What's the point of making a wave function? You want to see what's the response of the system to understand the phase.
I think I get what you're saying. I mean, it's a dynamical question, and I guess I'm not gonna I'm gonna give you a fuzzy answer in that we're studying things like dynamical phase transitions that you might not expect because there's no equilibrium state here, but there's totally different behavior in the dynamics. It's not exactly transport, I guess. Well, yes. Our measurement is basically energy eigenstates, and you can certainly take snapshots if you twang the system. Like you can prepare, like in an XY model, you can prepare one up and all the others down and just watch that defect move through the chain. And with these long-range interactions, and Alexei and others have shown that you can go faster than these Lie-Robinson bounds moving across the chain. There's something called pre-thermalization that seems to happen, that things sort of get locked into place, and you have to wait for the tiniest gap to let itself be known. And that's behind what's happening in some of these demonstrations of time crystals. I mean, all these weird phases are kind of coming out of the woodwork due to the fact that we have all this control. Many body localized phases that can underlie time crystals. So these are all a little bit scatterbrained ideas, but a lot of them come from condensed matter and indeed transport. So sorry, a little bit long-winded. Thanks for the help.
Last one.
Hey, Chris. I just wanted to add some comments on John's question and the second question. So it is indeed actually possible to solve for all normal mode problem in polynomial time, and you actually need the overhead that scales linearly in the number of qubits that you have in the system in order to actually do any XX gates in parallel, overlapping or not, while attaining the overall connectivity. It's just that if you actually go ahead and engineer the pulse in a more clever way, then you can take advantage of the locality that might emerge. That said, because you can actually solve for squarely many different XX gate controls, this could be one way to actually speed up the variational quantum eigensolver, because if you have many of the XX gates that you have to apply in parallel, you can actually do them on without losing overall connectivity on ion traffic.
Okay, so that's it. So we have now coffee break until 10:30. Let's thank Chris again.